So I'm going to get started with the title, Signal Processing and Expanding Graphs. And of course, I want to start by, of course, giving big thanks to Elvin, Samuel, and Alan. Alan was my promoter, and Samuel is a collaborator. One of the parts of the result we'll discuss is out of a collaboration with him, right? So, okay, graphs and graph signals. So, what are graphs? I expect everyone here to know it, but graphs are some tools or some kind of abstraction which you use to link similarities. So, different types of similarities can be pairwise, can be higher order similarities between agents or nodes, different entities. So, okay, one way to encapsulate the total relationship between them can be through graphs. And there are different examples of graphs, right? Like we have social networks, sensor and citation networks. And the main what graphs bring to a table is that they are like in time. You have a fairly directed. There's one way in which the information, yeah, it's fairly ordered, right? And even images and grids are fairly ordered, whereas graphs can be quite irregular or non-ordered. So that's what I mean when I say irregular here. So of course, it needs a different type of approach, right? And what are graph signals or graph data is any form of data which you can associate with the graph. Now you can associate data with graphs in different ways. There can be node level association in which each node is associated with some data. There can also be edge level or even various different types of association. So in this slide, we have some examples corresponding to so user opinions can be node level social networks. And social networks, you have humans. So humans have opinions. So yeah, that's like a fairly one-to-one node level association. And yeah, so once you have a graph, you can always find ways to associate data with it, right? And this just gives us a new way to interpret data, right? So we have graphs, we have data. What do we do when we bring them together? We can have graph data or graph signal processing. And what that does is, yeah, okay, we have the graph, we have the data. Now, can we make use of the data to do something, to reach some objective or some task which we need to do, right? So based on this, we have quite a few examples, and this broadly we call this graph signal processing based on what you want to do. So popular examples are filtering, in which like when you think of filtering in classical case, you eliminate some frequency bands, right? But so the same thing here, you have data defined on a graph, and you kind of eliminate or shape or attenuate different types of its different frequency components based, and this is of course done relative to the structure of the graph, right? Interpolation, also really popular example. You have missing values, you want to fill it, where in the graph this would translate into you have missing values at certain nodes and you want to fill it based on the structure and the data which you already have at node level or even at edge level for that matter, right? You can also do classification, which is you have graph, you have nodes. So, but you want to classify these nodes based on the data which you have on them, right? Like simple classification. So your objects are now your nodes. And you can also have this very different type of problem called topology identification, in which, well, you don't really have a graph, but there may be an underlying graph. And given you just have the data, and based on the data, you want to find out, okay, what topology is this data actually belonging to, or is there a topology, or yeah, how are my data linked to each other? That can give you an idea of the topology. So these are some common examples, and we'll focus on a few of these in the talk. And as an example of this would be rating prediction in recommender systems. So here, always think of a graph. So what are my nodes? So in this case, my nodes are users. And to build a graph, I need to connect users, and that is done through the similarities of the users. So if two users have rated some items and they're similar to each other, then you join a node between them, and this is how you build a graph. And what is your graph signal? So the graph signal in this case would be each node or each user has given a rating. So you look at all the users, all the ratings, and then there you have a graph. But in this case, the graph signal is defined for a particular item. So let's say for a particular movie, all users have given their ratings, you have one graph signal. The moment you change the movie, you have a different graph, or you can also have a different graph signal. So that's one thing just want you to be aware of, because this will come up later again. And of course, you have graphs, you have data, and what can be tasks here? So like we defined before, we can do interpolation, in which case you want to fill a value of a user, which means, okay, what rating would this user give to this graph? Because not all ratings are always present, right? And another thing could be topology identification, in which you have some users, you have some items, you know some users like some items, but you still want to figure out what users will like other items. So in this case, you consider a bipartite graph and you try to find the edges based on the data, right? And but what this talk is going to focus on is, of course, expanding graphs, and of course, the clue is there in the name itself. So you have graphs, but now they're expanding, and two things are happening here. You start off with a graph, and then the edges between the existing graph is changing, but at the same time, new nodes are joining, and that is also accounting for new edges, and this leads to a very dynamic scenario. Now, what's happened is a lot of pre-existing works on graph signal processing have focused on graphs of fixed size, in some cases with changing edges, but this is, so what the goal of this talk is to give an overview of some approaches which have tried to give a signal processing perspective of how to do the same on expanding graphs, like do signal processing on basically on expanding graphs, and give some, yeah, a somewhat unified view on it, right? And so there are going to be like three main challenges. So the first challenge has to do with uncertainty, and what type of uncertainty we're talking about here? It's the edges of the new nodes, can also be the edges of existing nodes. But what happens sometimes is you have this graph and you have new nodes joining in, but you may not know enough information about the new node. So you don't know how the new node is going to attach to the existing graph. So this poses a big challenge, because so far we saw that in order to have graph signal processing operations, it is always often very desirable to have the full topology connection. So if you don't have the new node, you cannot exactly account it. And in a real world scenario, this often comes up in recommender systems as cold start users, which are users where you want to predict something about them with your graph based, with your existing graph, but you don't have any information, no ratings, sometimes also no demographic data. So yeah, you cannot do much. But okay, but so that's one type of challenge. That's the first challenge. The second challenge is the streaming nature of data. So what happens here is, of course, uh, in many cases you would want to have lots of data, right? Because that allows you to infer, yeah, better. But the sheer nature of the data itself can be streaming, in the sense that it comes one at a time, and often so you don't have all of the data to work with together. So you need something efficient to work with here. Also, the presence of streaming data can become another issue if you have a delay sensitive applications, in which suppose you have one data but you need to update your model, but you have to still make some sort of a prediction because you can't wait for another data to come in. So in this case, you need to keep on making predictions, and this is this is just something which comes with streaming data, and we'll see how we can tackle them. And the third one is got to do with non-stationarity, right? So, and this leads to the streaming data case. So you have all these new nodes coming in, each has some type of data on it. But what you want to do is, okay, I want to make a prediction, but then the node which comes after that, and this is particularly more relevant in the case of recommender systems, because the new node coming is a new user, a new person with own interests and different type of data distribution when it comes to rating predictions over a certain type of movie. So what this indicates is you have a fairly non-stationary type of environment, in which the type of data underlying data distribution of the incoming nodes can also change a lot, and this would of course require more adaptive and more different types of signal processing algorithms, and yeah, we'll also try to deal with that, right? So okay, so three parts of this talk. The first one is going to focus on how to deal with. He's going to study a bit the how to deal with the case of not knowing the connectivity, right? And how we use GSP to deal with that type of connectivity issue. And we have two online approaches after that. So those two approaches deal more with the two other challenges that is of streaming and this non-stationarity thing, and we gear that at two important tasks over graphs, right? Some notation. So mostly calligraphic G for graph. When we use S, it's typically a shift operator. So it's a matrix representation of pairwise interactions between the graph. It is mostly sparse. So the off-diagonal elements are mostly zero, but when you have a non-zero, that means you have a node between I and J. And when we use X, typically that's a graph signal. And yeah, and examples of S are of course your adjacency and Laplacian matrices. So they are all examples of shift operators. And we have mostly, if unless specified otherwise, we have undirected graphs, and throughout we don't assume self loops. So that's we don't have any self loops whatsoever throughout the talk. Cool. So now we try to tackle the challenge one. So what happens when we don't have information? But before we get to that, so we need some tool, right, to do everything. So okay, the fact that we don't know the information is still there, those edges, but we still need a tool to process signals overall. So for that, and my choice, our choice was to stick to graph filters, and quick slide on why these things are useful. So think of this shift operator, right? This S matrix. So what happens when you multiply S with your graph signal is what happens is at each node, it directly combines signals from its immediate neighbors, because S is sparse, right? So the connectivity is encoded in that matrix, right? So when one shift, okay, you talk to your neighbors, not talk, but yeah, you gather their values. And this is happening at each node, right? So when you keep applying the shift operator multiple times, so then the same process happens, but then effectively each node has access to k hop information, which originates k neighborhood hops away. So what a filter does is essentially shifts up to a certain order, and then it weighs them and combines them through this matrix H. Sorry, through this scalar H. So the scalar HK weighs sort of gives some importance to the k hop accumulation, and then basically, yeah, you combine them and you have you have a graph filter. So it's parametric in the sense of H, because the HK now is like your parameter which is controlling things. It is localized because yeah, each shift is essentially happening locally. And yeah, and it's flexible in the sense that it doesn't impose any prior information on the data. You just have a parameter, that's it. And you can train it in different sort of settings as you can, and also for different sort of applications. They've been done a lot. And yeah, so there's a lot of work done on filters. But these are a specific type of filters. But and how do these work? Suppose this recommender system example, or you have user nodes, you have a signal which can be the ratings. So you start off with your input X, and then you shift and combine, shift and combine, shift and combine, and then you add them. And this is similar to how you do in with time. There's linear time invariant systems. There you also shift and combine, like this convolution. So that's why these things are also called graph convolutional filters, right? Now, okay, now we are going to deal with how to deal with the unknown connectivity, right? So we have V plus, which is this new node, which has joined, which is there, but we don't know how it will connect. So how do we model its connectivity? How do we say something about it? So what we assume is, okay, let's model its connectivity in a random way. That is, we assume a vector A plus, which is going to define how this connects to the existing graph, and we assume this to be a random vector, right? And this random vector has this particular characteristic that each element of it is random, but it has a certain weight with a certain probability. And what this means is that each the new node, it will attach to an existing node in my system, in my existing graph, with a certain probability. And when the attachment is made, you will have a certain edge weight, right? So this is all there is to it. This is so this P and W kind of dictate how your new node interacts or connects with the graph, right? And you collect them in these weight and probability vectors, right? And since A plus is random, right? So whenever you sample from it, so the updated adjacency and Laplacian matrices are also going to be, well, not fully random, because A is still known, but then you have this uncertainty in your system, right? And once you have your adjacency and Laplacian matrices, these are also examples of these are now like shift operators, right? And once you have shift operators, you can plug them into a filter, right? So from now on, we'll be looking at how you design, how you can design filters, but how this affects learning with filters, let's say, right? And since A plus, each is element-wise independent, so that allows us to write the expectation of the vector and its covariance, which in this case, yeah, you have diagonal because you consider them to be independent, but you can make things more complicated here, of course. And of course, like a natural question is, okay, you take this WNP, but okay, what is a good WNP? And there can be so many ways to look at it. But in our case, since we are focused on task dependent, we say, okay, a good W and WP depends on what task you want to do, because this is GSP and we are ultimately looking at task like yeah SP tasks, right? And so that's what we want to do, right? We fix a task and then we find a WNP which learns the attachment behavior of these new nodes. And a small example of this would be, so let us have uh, an existing graph signal X, and we want to predict the new signal at the new node. And yeah, and we have, let's say we have already a filter which we want to use, and the goal is, okay, how do we learn this for predicting a new loss? So this is like a direct mapping between a task you want to do and how to yeah learn WNP for this process. And of course, we want to learn it, so we need data, we need data driven things, we need to minimize a loss function some point. And the key idea, before we move into the optimization problem or the formulation of it, so the key idea here is, you have your existing graph with these edges in green, and these three nodes you see, the three colored nodes with the red edges, since we are learning from data, we need a training set, right? So these are essentially the elements of your training set. So we have an existing graph and we have a batch of new nodes, and for each node we have the red, which is their attachment, which is known, and the signal on them, which is also known. So we essentially use that information in learning. And what this boils down to is, we learn from how other new users have already interacted with the network. So in order to predict or make something about, make some predictions or do GSP with future new users, we use the behavior and the attachment and rating of the other users to help us. And that's how that's like the key idea, right? And this is okay. So of course we have a batch with own attachment patterns and signal X, and this leads to an optimization problem in WNP. So you see that we are minimizing a loss, subject to some constraints on P's are probabilities, and yeah, so they have the respective constraints. Now you see that we have an expectation here. So that expectation is because you want to ultimately predict learn the model attachments, right? So we use the attachments as the true attachment information as regularizers, but to learn the attachment behavior, you still need to use the expectation. And the F function is basically the task aware loss. So what do you want to do? You want to classify that you'll have some SVM or some classifier type of loss. You want to do yeah regression, you have least square loss. And the functions G and T are some priors you can attach on the P's and W's, like you can have L1 norm, L2 norm, if you want sparsity, if you want, yeah, so this is fairly general, so you can choose what you want there. And typically, this is going to be a non-convex problem in both W and P, and even in P itself. And typically, the strategy to learn with this is use an alternating approach, so that you update your weights and then you update your probabilities, and yeah, and you need to do projected gradient descent because of the constraints. And yeah, so because of some things, the convergence and the perturbation behavior of this is covered in the paper. I'm not going to go into that here.
So the X's and the X and X plus is also different for every training sample. Is it like, should it be XD and XD plus? Or?
Yes, yeah, you're right. This will be XD plus. So the X is fixed. Let's say, like the existing graph has the same. It's always the same. But you can also have different instances in principle, yes, but that just gives you, well, in one of our cases, that X is also XT. I'll come to that in evaluation. But yeah, in this case, it should be XT plus, because each new node, T here is index for the new node.
I thought training sample. Is T not the training sample, that you have different H?
Yeah, sorry, a new node is the training sample. So the training, yeah, you're right. So how do we compare? Okay, so the first thing is that this is some type of attachment or some type of probabilities which are task aware and topology aware as well. So the easiest thing to do was to compare this with some heuristic approaches, which are, well, also in some cases not aware of data or task. Like the uniformly at random association would mean that you form edges with each node on the graph. You have an equal probability, and what this means in recommender systems is that, yeah, you are going to give every user some importance, every existing user some importance, and this way you can get more random, more diversity in your predictions. But if you have a degree based preferential attachment, so in this case you are likely to connect to a user who has more degrees, and in recommender systems this means that you are likely to form associations with users who have rated a lot of items, because if you rate a lot of items, you've seen a lot of movies, then you're likely to have more edges with existing users, right? So these are some heuristics which kind of make sense that, okay, like so there's some equivalence with recommender system prediction. And we also have this database attachment in which we learn empirically the probabilities from data. So since we are dependent on a training set, it can be that some in the training set we observe that some nodes are being preferred by the existing nodes. So we learn empirically the probabilities from that. But of course, it depends on the training set quality, right? And so for synthetic data, Ardoshreni and Barbarzal, apologies for the spelling on those things, on those two names. But yeah, so we typically use them for synthetic data to see if at all we have something. And for movie lens data, yeah, that's for recommender systems. And we move ahead, and then yeah, so with synthetic results, so yeah, the first row is just convergence plots, but in the second one for synthetic data we try to find the mean square error for making some predictions on a new node, and these are graphs of 1,000 nodes, and we, of course, the existing graph is fixed. We always take, and we have like a bigger training set. So we see that like the preferential and uniformly random attachment that doesn't do so well. But this approach, of course, it makes sense that you combining the W and P, and you're going to get better results for making a prediction, right? And typically, what you also found was that this L2 regularizers work better than L1 regularizers, so you don't want sparse P, at least for the synthetic case, sparse P and W did not help. And of course, training them jointly is more beneficial. But now this recommender system example, I'm quickly gonna. So what we do here is there are like 900 plus movies, right? So for each movie, we build this graph of 50 existing users. So okay, we have lesser users because the total number of users in our data set is in this case is sorry, the total number of users is 943. But since in this case we have to divide our users to existing, our new training users and test users, so we could not, yeah, and since we need more training users, so that's why we have like relatively small number of users as our existing graph. And then since we make each graph signal is for each movie, and each way like thousands, 1,700 or so movies, so you can train in principle one for each movie, and that is what we call personalized rating. But since we can't show the results of all the movies, I decided to take 6 items here which have different, which differ based on how many training data you have, and yeah, so which based, because each movie also doesn't have that many ratings, right? So based on that, just to show different types of items, we show this prediction in which, of course, lower error is better, and we also trained on all the signals together. So this would correspond to what you mentioned, the bold X with a T. Now you have a different XT, and you also have different XCs on those things. So typically, we see that personal rating is really favorable because then you focus on a graph. It has its own distribution, its own task, things that are way better here. But the problem is, you see, when we consider all items, the gaps shrink a lot. And of course, this happens because now you're trying to train probability attachments and weights for different graphs, and that may not always make sense. So even though it's still better than the other things, in recommender system, I think small differences are also important, but in terms of error. But of course, this clearly shows that you should try to stick for personalized training.
But the graph is also like, you have one graph for a particular movie, or?
Yes, each movie has a particular graph.
How do you design that graph?
So
nearest neighbor of what?
Nearest neighbor, 35, nearest neighbor graph.
What nearest neighbor of their ratings, or?
So
when do I connect to users when they have the closest ratings? So
yeah. So you
35 closest ratings.
so the way it's done is you have the existing users. So we set a threshold of, so of course we divide a number of items based on which I calculate each user's cosine similarity or some other kind of Pearson based similarity, and then based on the similarity 35 closest users.
If we connect everyone, and then you keep them.
Yeah, and then
But for a particular.
yeah, and then for a particular movie, there's a paper based on which this is done. So then you remove some of the edges based on who's rated. Right? Okay, so I'm gonna skip this, I guess, in the interest of time. In general, more details. Yeah, so there was another paper which here you try to learn the Revolution piece, but there's a paper in which you fix the, like, you try to for more focus on learning the filters, and that's there in this other paper which I cited here. And yeah, and also we had a master student who did extended this to do some results on graph convolutional neural networks. Yeah, but okay, cool. So I'm gonna move for in the interest of time. Right. So now what we saw previously was that we had this training with replacement kind of thing, right? In which you have this batch of nodes, you pick one and then you take it out again, because that's how we wanted to study more the attachment thing in itself. But of course, that is not always super realistic, because we have cases in which, like this, in which we have new users coming or new nodes joining in, and we want to make a prediction, and then this node is absorbed into the graph, and then we have another node, and then that node we need to do something with it, and then that node is also absorbed into the graph, and now we are getting into, again, like the time varying nature of data, and we also have this delay sensitive applications, and but most importantly, now once a new node comes, it stays in the graph, and then so the graph is now keeping, basically it's growing in size, right? And again, this brings back to the two main challenges we had, right? The streaming nature of the data, right? But in this case also, we can also have lack of connectivity here. So when a new node arrives, we may not also know if it's going to connect or not. And this again, so this adds again another layer of difficulty, let's say, right? And we are going to now see how we try to tackle this problem overall. But of course, we're still going to use the stochastic attachment rule which we used. So what do we do in very short summary? So we train the graph filters now, but now we do it online with each incoming node. So if you don't know the attachment, we use a stochastic attachment rule when a new node information is not known. And this is what discussed before. And we also have an approach in which we adapt the stochastic attachment. And I'll come to that. And then we do some performance bounds with respect to the known attachment patterns. I'll go through them of course, when I get to it. Right. So we start with the graph. G0 with, so the starting point is known, it's always a graph. And then we have a T sequentially incoming nodes, right? And for each node, we have this signal which we want to predict in this case. And we also have a vector AT now associated with each incoming node. And this AT is known, but in some cases it's also not known. So we have two different approaches right there. So, and we consider directed connectivity of this node. So this is because if we want to really focus on making predictions at an incoming node and don't want this node to affect the existing nodes, then we went for this type of an update, which of course means we needed to keep this that part now becomes 0. And AT plus 1 is also directed. In recommender systems, yes, in most cases, we also have this directed shift operators. Right. So what do we do here in the case of stochastic attachment? Yeah. So this was directed attachment, right? You have AT, you add it, and then you process, you do your filtering, and you move on. But in the case of stochastic attachment, like we had a probability vector and a weight vector, right? So now this VT also has a probability vector and a weight vector. So the subscript T here just denotes that this probability vector is now going to grow with time, because the number of existing nodes is also growing with time. So that's why we have the time varying nature in this thing. The others will also apply. You still have the statistics which are valid at that instant. And our parameter of interest now here is this graph filter, which you're going to learn, or rather update. And yeah, so the output at the new node, you can also write it down once you plug it into the expression of the graph filter. And this is the output which is deterministic for a deterministic case. But if you have a stochastic case, then this AT is random, right? So then you need to analyze it in its expectation, right? And now we go into what essentially happens in online graph filtering. So at time t, we have the new node. If AT is known, we attach it into the graph, we update it, and then make the prediction. And if it's not attached, then we make the stochastic prediction, which is the expectation. We have the current filter, which we had at that time, and we use this filter to predict, okay, what would the value be at this node, right? And once we make this prediction, the environment or the loss which we made on this prediction is revealed to us. Now, the assumption here is that the functional form of the loss is known. Like we have this LT, which has FT and R. R is a regularizer on my H, and FT is the loss you incur for making the prediction for XT. So we know the functional form of the loss. And what that allows us to do is it allows us to update my filter from HT plus T minus 1 to HT, right? And yeah, so this is what we basically keep on doing. But in the stochastic scenario, AT is revealed after you make the prediction, because the assumption is, yeah, we may not always know the scenario, what the true prediction is, but then, yeah, after we make the prediction, we can reveal the AT and then absorb it into the graph and wait for the new node, right? So yeah, this is basically what's happening. Okay, so in the deterministic case, we just plug in a loss function, which is this regression type loss with regularized least squares. And the update is a projected online gradient descent in which you are here at HT minus 1, right? And then this loss, so the most important thing here is the loss is just based on what you observed recently, right? And then you take a gradient in the direction of that loss. And yeah, so you move just one step based on the most recent loss you have, right? And then you project it onto some set of H, which so you need some convex set on which to project. And yes, and this has a complexity of the number of edges which you have, and case the filter order is because of how you calculate the output in graph filters. All right, and you have stochastic online filtering. So in this case, you fix a predefined PT and WT. What this basically means is, as long as the algorithm keeps running, you fix, okay, my PT is always going to be uniform attachment based, or my PT is always going to be degree based attachment. The rule itself will not change, but the values in the PT will change because the graph is growing, right, based on the existing structure, right? So the rule is not changing. And now again, we have this expectation on the loss, and then we do projected gradient descent again. But the potential drawback here is that since you fix your PT and WT, or the rule, attachment rule, yeah, you don't get the chance to update it later, maybe. So one reason we thought was, okay, why not we make this part adaptive as well? So to do this, the goal now becomes, okay, in addition to doing the online filtering, we also try to update PT and WT, right? And to do this, we have a dictionary of attachment rules. So based on things like uniform degree based eigenvector centrality. So based on these metrics, we can take some dictionaries, and then we weigh them through this parameters M and N. So now M and N can be updated to account for the PT and WT. So at each step now we do projected gradient descent with H, M, and N. Yeah, and this incurs more complexity. You see now that the complexity already is depending on NT because of this stochastic nature. But yeah, this is just how it comes out, right? So now these are algorithms, and always when we are doing online algorithms, there is always interest in this thing which is called a regret. And what a regret is basically is, if I knew all the streaming information, and if I trained a filter based on it, then yeah, how would my system behave? So and then what type of loss? Because you see, this is accumulating the loss across time t. So yeah, the loss of your online filter with this oracle filter H star, and you combine it, and then you see it. And typically, okay, once you have a regret, typically you want to bound it with the upper bound. Why? Because this gives you a worst case prediction, a worst case analysis of how far you are away from this thing. But again, this is worst case, right? So in this case, we have two cases. So we have this pretty standard, honestly, the deterministic regret, in which your regret now, this is when the attachment is known. So this depends on this LD term is like the Lipschitz nature of your loss function. And yeah, so, and this shows you that, yeah, typically you will have, there are ways to play around with this, like minimize it, but I'm not going to go into that. But the more importantly, in the stochastic regret, so now there are two types of analysis going on here. The first is, of course, the not having all the data together. So that is, you see these two terms are already coming up here. And whereas the other terms are coming from not knowing the true attachment when we are making a prediction. And you see the terms which are highlighted in red are coming from the stochastic attachment model. So this you can give you some insight as to what type of PT you may want to use if you want a lower regret bound. WH is the maximum weight, edge weight you're allowed to give. This depends on this on the second order statistics. And this term here, it also gives you, if you ran a deterministic filter and a stochastic filter at this from the same starting condition, also the average, the distance between them also plays a role. So these are things for further analysis. And yeah, so in this case, we have some results where we compared with batch filters, pre-trained filters, and some kernel-based methods, which are also like an online kernel-based methods, which are nice alternatives to filters, but they make some prior assumption about what type of kernel you use. So in this case, yeah, just and of course we also have this PCOGF, it's a prediction correction based online filtering, in which we, in the stochastic case, we do a stochastic prediction and a deterministic prediction. So its result is always a bit in between the DOGF and SOGF. And it gives you an idea that, okay, how much of the attachment is really helping you, let's say. But typically, the takeaway of the slide here is that typically the DOGF, of course, since it does better, but in some cases, I think the stochastic approach can be close, or yeah, I think the gap is even smaller in real world data. And in this case, we compare the stochastic and the adaptive stochastic method for the normalized cumulative regret. So the regret is itself grows, of course, it's going to grow with, expected to grow with time. But if you normalize it, you would expect it to go flat at some point. So in this case, we see that, yeah, the adaptive goes flatter at a lower error. So can claim that, okay, it's learning in a better way. This adaptive thing is helping in some way. In this case, you see that it starts high, but then it goes lower. Yeah, so this was typically, yeah, more details are, and we also extended this to growing simplicial complexes, in which now we are trying to predict edge flows and not necessarily like new nodes. So there are new edges and new edge. Yeah, you have a growing simplicial complex there. So we have some, basically the extension of this is there. And yeah, okay, and this is it. And how much time do we have? Because 5.
So you go to 31. Can I ask the question?
Please.
So the last two terms in the deterministic have a t in the denominator, and in the stochastic they have not. Does it mean that the bracket should also include those two last terms?
I think the t
is a error somewhere.
Yeah, because I think what's happened here is
Bracket should be.
I think this bracket should go all the way to the end. Yeah, thank you. Thank you.
I'm paying attention.
Yeah. Okay. So now we are in online topology identification. So what we did was more SP based online approach, but this is online topology identification. So what topology identification essentially is, just look at the figure. You have some vectors, right? X1 till XT. And based on this, you want to infer the graph, right? That's simply what it is. I'm going to move a bit faster now. But in our case, what we now have is our X1s and XTs, as you see, they're growing in size, right? And based on that, now we want to also predict these graphs, which are also, yeah, have graphs with new nodes. So what we are trying to do here is also keep track of how the starting nodes, the edges between them can also change, right? But we also have to take into account the new nodes, because yeah, there are new types of new edges also which are being made there, right? So this is extending it to this more complicated scenario. right? So how this is done when you have fixed number of nodes is you have this matrix X, you have T samples, you have this matrix, and you try to estimate the shift operator based on minimizing a loss function. So this L loss, calligraphic L loss, what it does is, so you need to use your data, right? And in certain priors, like of course you put some priors also here on your data, which I forgot to mention. So in certain priors, you need the sample covariance matrix of your data, and that relates to the shift operator or to what you're trying to estimate. And since you want sparsity, you typically put an L1 norm, and then you solve it, right? And there are plenty of works on this. I've provided a link to one of the papers which goes fairly well into it, right? So this is the standard case. But in our case, of course, at time t and t plus 1, we can have new nodes, right? And typically we assume in this paper that always one new nodes add, but you can always extend it to multiple nodes adding, and we have that in the results. And so what happens is at time t plus 1, so you have the st plus 1. So this has already the existing nodes, and you have 3 different parts in the block matrix, right? So you have edges between the new and the existing nodes, and you have edges formed purely between the new nodes. And you also have the graph signals which are coming from those new nodes, right? And one thing we want to do to solve this problem is, I mean, one way to do this is at time t. So when a new node arrives, you want to update the sample covariance matrix. Now I'll go in another slide. I'll explain how that happens, because now we have an extra dimension, right? So to extend how this approach in this setting, you need to find an update for the sample covariance matrix, and then you need to plug it in. But now you have this new term in the loss function, which kind of controls how much this, like the existing links change. So because ideally we want that, okay, whatever links exist, we don't want them to change a lot, whereas the new nodes can, yeah, we cannot, yeah, they can be more expressive, but we don't want that thing to change so much, so that alpha kind of controls that, right? And typically we can run this whole thing in a solver, and it's typically slow, but it does provide high quality estimates, but it is slower, and it is not fit for delay sensitive applications, because then we may have another node coming in. So the main goal is, okay, how do we make use of online learning to update our S in this case, basically, right? And how we do that is, of course, so now the step of updating the sample covariance matrix. So this xt transpose is our latest sample. So that is you make a Hadamard product of that with M2, which is a mask. So that kind of gives more, you can choose how much importance to give to more recent samples, whereas you have another mask M1, which weighs the existing samples, but there's more intricacy there, which I'm not there, but is there in the paper of how to select and how to weight it. That those are things which can be tuned. So of course, since in online learning we always have a loss at time t, so we have our loss ft, which in this case is the loss which we had, and the type of update step is again a projected gradient descent. But since we can't make the gradient here because we have L1 norm, which you can't take a gradient of, you need to do a proximal gradient, which is you take a gradient based on the differentiable part, and then you have a threshold operator, and then you project it. So this is our update step, and we are projecting onto the set of nt by nt how we want that S matrix to be. So this will now change depending on what you are estimating, right? And then we combine this update with the update which we had before, and there are some, and of course you're right in asking that, okay, there's a change in dimension, right? So how do you add these two things? So we do zero padding there, essentially, and that, so the bar, when we see a bar, it means that there's zero padding happening there. So in the Gaussian case, so this is an example, right, of the framework we just used. So this is if you have a Gaussian, the regularized likelihood, this is how you would solve it. The projection would look like projecting onto PSD matrices, and and then you would keep on going, right? Yeah. So I'm going to skip this. And of course, like in all online learning cases, you also have a regret here. And the regret, the cumulative loss is again, but there's a difference here. The difference here is that each time we assume that we compare with the true graph at each time. Previously, we had a H star in the filter case that was like static regret, but this is a more a dynamic regret because the optimal solution itself is dependent on time. And we showed that this regret or this bound, it depends on a constant plus this term. And what this term is basically how the optimal topology itself changes. So it's like, because of course, like the optimal topology is always changing, right? And yeah, since you don't have a kind of control over that, so it makes sense that why this type of term would come up there. And this often comes up if you look at regrets of dynamic cases. This term often comes up. So it was nice to see that even in this expanding scenario, we got something similar. And yeah, so in terms of results, so we have Ardo-Sheney graphs, and we, as you see, we have two types of frequency settings. So the blue plot corresponds to one time case where we added 20 nodes, whereas in the red plots we add small number of nodes, but it's like that you have more dose of that. So this was just a way to show the two different scenarios. And in this case, okay, I should have, yeah, that's not the right figure on the right side. But I think typically one figure is enough to understand what's happening. So this is like the error. You see that it's tracking quite well. Of course, there is a disturbance, but then the errors start going down, and this would mean that the regret would also start to stabilize. And in COVID data set, yeah, so what we did here was we have the US states and territories. So those are the nodes of the graph. And the incidence rate, what the incidence rate kind of tells us is it is a median of the total number of COVID cases over the graph signal. So this is one way of representing how the graph signal itself is changing over time. Through this type of plot at least. So what you see is in this region from the two black dots. So here the growth is like this, right? Whereas in these cases the growth is not so much. So since the growth is a bit more pronounced here, if we run our approach, we see that the error also spikes up quite high, but then once the growth here it's a bit more stable, then yeah, the regret stabilizes, but the error also comes down, right? And in this case, of course, we are comparing to the true graph given by the algorithm. There is what is a true graph, of course, is a matter of debate in these type of approaches. So yeah, so there was just showing some of these things. Overview, I'm going to skip that. So now finally, I'm going to just wrap up in this slide. So SP-based principal framework for expanding graphs, at least with graph filters, but of course it's we have some results on GCNNs also. Yeah, so the stochastic attachment model allows us to play with cases in which we don't know the connectivity. We can also adapt it. They can, yeah, and these two online approaches, one for GSP, one for topology ID, which we think are good like contributions to the field. And yeah, it's still well compared to to known topology. And the performance is relatively well. And so the challenges are okay. When I say relatively well compared to new topology, it is from some results in which we compared performances of not knowing the topology and topology. That's why I mean we still there is not a huge drop off, let's say, in performance. And of course there's some challenges, right? Another big challenge is modeling data on expanding graphs, because you have this. Doing a state space model could be a challenge because the dimension is increasing. So like for example, and I think you need more spectrum based approaches where, since the graph spectrum, it's you need I think more ways to model these things, and more defined stochastic attachment models. Maybe Bayesian approaches can be a good approach to give more rich probabilities and get posteriors and those type of things. And another good thing is you can also expand this to higher order networks. So yeah, that was it. Thank you. Yeah.